When asked what energy efficiency is about, most common answer people give is it's about energy saving. However, the meaning of the term efficiency is not the same as the meaning of saving. According to Cambridge Dictionary, efficiency is the quality of achieving the largest amount of useful work using as little energy, fuel, effort, etc. as possible. Most specifically, in architecture, energy efficiency focuses on designing built environment that prioritizes the reduction of energy consumption without compromising any comfort or functionality. The history of energy efficiency began in the mid 19th century as an academic and policy concern in highly industrialized Great Britain. A pivotal moment was the release of the book The Coal Question by Stanley Jevons in 1865, in which industrial revolution's high dependence on fossil fuels was noted as becoming increasingly scarce. Energy efficiency, as we know it, as a systematic, science based approach, was set in the 70s of the 20th century, and it was a response to the price shocks following the Arab oil embargo. First, all the measures were focused upon transport as the biggest fuel consuming sector considered, but very soon after that, building sector became largest priority of energy efficiency. One of the most recent studies upon energy consumption by sectors showed that buildings are still the largest energy consumer. Special attention is paid to the residential building sector and to reducing energy consumption for space heating, space cooling, water heating, and lighting in residential buildings for one single reason. Unlike public buildings and industrial buildings, residential buildings are considered economically non sustainable since they only consume and they do not produce any economical profits to um, pay for the energy they use. Energy efficiency in architecture includes integrated processes covering two method groups: passive means and active systems. Passive means group concerns built environment organization and includes using nature elements, space organization, silhouette design, form factor, used construction materials, direct and indirect passive systems. And all these methods, these measures, have to be considered during the design stage. In this group is also included effective insulation, although it can be applied later after the building is finished. Active systems are added afterwards and just need adaptation to existing elements and space organization. Their purpose is to replace conventional systems with ones that consume less energy or use alternative energy sources. Such systems are solar panels, photovoltaics, thermopumps, wind turbines, biofuel generators, and others. The areas of application of energy efficiency in architecture can be at the stage of urban planning, at the stage of site organization, building organization, interior design of a single room, and of course the materials of the construction elements. The living comfort aspects energy efficiency in architecture deals with are the thermal comfort, which includes warming and cooling, lighting comfort, that includes natural lighting, its distribution, and shading if needed, artificial lighting, and visual comfort. So the lighting should be not too much to tire the eyes or too small quantity so the eyes to get too frustrated to see. Air quality, which includes natural ventilation, both casual and controlled, forced ventilation using different systems, and air humidity and composition. And the last group of aspects is the acoustic comfort, and it's the newest trend in energy efficiency, and it includes controlling airborne sounds, controlling structural noises, and providing the best acoustic for the room and the functions that happen in it. Some basic processes and terms energy efficiency works with three kind of energies, usually transforming between themselves, are the heating energy, electricity, and electromagnetical solar radiation, and the ways to transform one of these energies into another. As an example, when we plug the radiator in electricity grid, the electricity warms the radiator and it starts to produce warm energy. The other process energy efficiency works much with is the exchange of warmth. It happens between objects with different temperatures. The larger the difference is, the faster the process of the exchange goes between the two objects. As the temperature of the two objects become closer and the difference becomes smaller, the speed of the process lessens and the exchange of the warmth becomes slower until theoretically both objects became with equal temperature. The third process, very often used in energy efficiency, is the change of the aggregate situations of the materials. There are three aggregate conditions: hard, liquid, and vaporized. And very important facts that when passing from lower aggregate condition to higher, as from hard to liquid or from liquid to vaporized, materials need much more energy and consume much more energy than just to get warmer and just to increase their temperature but keeping the same aggregate condition. And the opposite, when changing from higher aggregate condition to lower, the materials, the elements reduce much more energy than they reduce when just lowering the, their temperature but keeping the same condition. This process explains the short periods of warming in the autumn and the short periods of cooling in the spring, because in autumn, when the north hemisphere starts to cool, the water on the North Pole turns into ice, which means it goes from higher condition, aggregate condition, to lower, and it reduces some warmth energy to the atmosphere. And vice versa in spring, when the heating process starts, the ice begins to melt, and to keep the process of melting, it uses, except solar radiation, it uses also warm energy from the atmosphere and extracts some warmth from the atmosphere. So this causes the short periods of cooling in spring. The next moment in energy efficiency is the connection between the mass and the accumulating possibilities of the materials. The heavier, the most denser the material is, and the more thicker the element is, the more mass it possesses, the more warmth energy it can consume and keep within itself. And after that, reduce it to the surrounding air. And the opposite, the thinner the element is and the whiter the material is, the less warmth it can keep for long period of time within itself. And the last important moment is that active insulation usually is placed only around rooms in which there is an active heating or cooling system. It's not wrong to cover the whole building with active insulation, but additional factor here is so-called economical efficiency, because what is seeked as the end result is that the sum of money given for the quality of the quantity, of insulation put on the building is supposed to pay back and even to produce some profits in the period in which the insulation is working properly. Because each kind of insulation has its life period, after which its efficiency falls significantly, lessens, and it's not that efficient anymore. The aim of the thickness of insulation different thicknesses on different places of the building is to achieve an equal radiational temperature of the inner surfaces of the rooms, such as the inner surface of the wall and the floor and the ceiling, to be equal in a given room. Actually, the need of energy efficiency occurred with the very first human built shelter, and up to a very recent period historically, um, if one needs to chop the wood for the winter to keep the house warm, the need of a house that will get warm as soon as possible with less possible timber and keep that warm as long as possible definitely was required.